So a random variable is going to be a central component of our study, and it's just the numerical output of an experiment. Maybe think of some function of the sample space into the set of numbers. So random variables come in two varieties as far as we're concerned. They actually can come in lots of different varieties, but for our consideration, they're going to either be discrete or continuous. So discrete random variables are ones that can only take an uncountable number of possibilities, and continuous random variables can take any value on the real line or some subset of the real line. And so in the discrete case, it makes sense to write this probability x is exactly k, whereas in the continuous case, it makes sense to maybe write the probability that x lies in some sort of region. So here's some examples of things that can be thought of as a random variable. The 0-1 outcome of the flip of a coin, if we code, say, a tail is a 0 and then a head is a 1, then our outcome, 0 versus 1, is a binary random variable. And we'll talk later on about how to describe those. So the outcome of a die roll is, of course, also a random variable. How about the BMI of a subject 4 years after a baseline measurement? We're going to model that as if it were random. The hypertension status of a subject randomly drawn from a population. Again, we're going to model that as if it's random. So it's very useful to have these ideas of things that given the possible values that a random variable can take, gives you the probabilities. So we have to differentiate between the discrete case and the continuous case. In the discrete case, we talk about probability mass functions. To be a valid probability mass function, it has to be bigger than or equal to 0 for all the values that you are willing to plug into it. And the sum of all the possible values, probability of all the possible values, has to be 1. So oh, and I'll go through an example in a second. Oh, no, here we go. Here's our example. Okay, let's just do our coin flip. X is 0 represents tails, and x equals 1 represents heads. So we might write our p of x as 1/2 to the x, 1/2 to the 1 minus x for x equals 0, 1. So if we type in p of 1, we get 1/2 raised to the 1 power, 1/2 raised to the 1 minus 1 power, which is 1/2. And if we plug in p of 0, we get 1/2 to the 1 to the minus 1, 1/2 to the 0, 1 minus 0 power, which again is 1/2. Okay, so that's exactly what we want. It assigns 1 and 0 to probabilities of a half and a half. And there's a lot of different ways, I guess infinitely many ways, you can specify this probability mass function, but this is a particularly convenient one. Let's do a slightly more complicated version of the same problem, but imagine if the coin is not fair. Let's suppose the probability of a head is theta, where it's some number between 0 and 1, right? So there's maybe a 25% chance of heads and a 75% chance of tails. All right, so let's type in p of 1, or write out p of 1, which is theta to the 1, 1 minus theta to the 1 minus 1, which is theta, and p of 0, which is theta to the 0, 1 minus theta to the 1 minus 0, which is 1 minus theta. Okay, so it works out, right, that sum of these two is going to be 1. It's always greater than 0, provided theta is greater than 0. And so, or between 0 and 1. And so this is a nice way to define a probability mass function specifically for the binary case. And you'll see later on why we do it in this specific way, as kind of multiples of theta raised to the power of x, why we do it that way. Okay, so that's the discrete case. The continuous case, we need something that defines probability. We have this problem, though, that in the continuous case, if we're modeling it as continuous, right, a specific value of a random variable, the weight of that function is going to be 0. So what we wind up defining is that a probability density function is just some function where here's 0, has to be some function, has to be bigger than 0, right? The total area underneath it has to be 1, okay? And then probabilities corresponds to regions under the density, right? So if you want the probability that x is between A and B, it's going to be that specific area. This then implies, right, the probability of a specific value is the area of that line, which is 0. So the probability that a continuous random variable takes on a specific value is 0. But that's a consequence, that's merely a consequence of modeling modeling the probability as modeling x as a truly continuous entity, right? It's an infinite decimal expansion at that point, and then it makes sense that it would not take on a probability value for a specific value, because we don't ever record things with infinite precision. So it's okay for that property to be true. So anyway, the central rule of probability density functions, the most famous probability density function being the Gaussian, this is the bell curve, right, is that areas underneath it correspond to probabilities of the random variable. Let's go through an example. Suppose that the proportion of help calls that get addressed in a random day by a helpline is given by this probability density. F of x equals 2x for x between 0 and 1 and 0 otherwise. Okay? Is this a mathematically valid density? Good question, Brian. Thank you, Brian. Let's see if we can answer it. Okay, here's what it looks like. I plotted it. And I think it's pretty easy to show that this is a valid density. So it goes up to 2, and it goes from 0 to 1 right here, right? So it's a right triangle. So the area is 1/2 the area of the base times the height. The area of the base is 1, so 1/2 the area of the base is 1/2 times the height is 2, so the area is 1, okay? So what does this say? This means that the probability that the proportion of calls, let me go back and just remind us how we defined what the process, the proportion of help calls that get addressed in a random day, okay? So what does that mean? That means this area right here, what percentage of days do, say, between 50 and 75% of the calls get addressed? What's the if the days are a random sample of days, right? What percentage of days is that true? Where between 50 and 75% of the calls get addressed, it's going to be that area as given by this density. Okay? That's what modeling this process with this density would suggest. And it's kind of a silly density, right? You wouldn't model this process with this density, right? It would be weird for the percentage of call volumes getting addressed to follow a density that looks just like this. But it's nice to work with for our purposes because we can calculate areas and stuff like that just using triangles. What's the probability that 75% or less of calls, fewer, right? 75% or fewer of calls get addressed? And that would just be this blue shaded area right here, right? Here's 0.75 to 0. We want that probability, that area, okay? So here I actually go through it, right? Just remind ourselves the density itself is 2 times x, right? So this height right here at 0.75, that's 1.5, okay? So it's the area of the base is 0.75 divided by 2. Area of the base divided by 2 is 0.75 divided by 2. Then times the height at that point is 1.5 using our little triangle formula, and that gives the probability of 56%. By the way, this density is just a special case of the beta density. And so you can actually, in R, if you have any density and it's called den, then Pden of x will give you the probability of being lower than x for that given density. So this is a beta density, so p beta of 0.75, and here's the specific parameters that I use, gives 0.5625.